Alright, physics, let's do this thing. We have some last second review. Well, last second. Some like day before review, right? You know, the quiz coming up. It's on any force that there could be. So, what I have here is just a collection of forces practice. I'm going to go through this. I'll also try to post... Yeah, I will. I'll be able to post these pictures that I'll do as secondary check, right? So you can check just the work, or you can watch the video. So, first question is kind of like as broad of an umbrella as we can put over forces. So 4 forces act concurrently on a block on a horizontal surface, as shown right there. So 80 down, 80 up, 100 right, 120 to the left. And as a result of these forces, the block does a thing, right? Because these two forces are not the same, these forces are not balanced, this object is not in equilibrium, which means I can't do this. I can't be moving at a constant speed to the right or to the left. So choice A and choice B are off the table. Not in equilibrium. So it can't be constant speed, right? We know that the force on the left is bigger than the force on the right, so we must be accelerating towards the left, and that's all we know. I actually don't know if it's moving to the right or moving to the left, because this diagram, which is a free body diagram, it shows all the forces acting on an object. It does not tell us velocity. Velocity is not a force. It's a vector. It tells us something about our object, but it's not a force, right? Moving on to number 2, we have an 8 Newton wooden block sliding across a horizontal wooden floor. So I have a wooden block on a wooden floor. So I need the force of friction, and they tell me that it's kinetic. So I know the force of friction is mu times the normal force, which means in this case that it's 0.30 times 8 newtons. So this is the weight, or the force of gravity. And in this case, right, if I have a wooden block, and I know that the force of gravity is 8 newtons, then I know that the normal force, right, force of gravity has to equal the normal force. So I do the math, and I get 2.4 newtons for choice A. Easy enough. Number 3 is a little more difficult. So I have, they give me the frictional force is 1.2 newtons. I want to know what is the coefficient of friction. And they tell me this. And the important thing to realize, this is mass. This is not weight. Right? We said a little earlier that the force of gravity and the normal force, right? The force of gravity equals the normal force. But if I want the force of gravity, I have to do mass times the acceleration due to gravity. So I have to do 0.5 times 9.81. Now that is 4.905 newtons. Right? That's the force of gravity, which equals the normal force. So now, I can do force of friction is mu times the normal force. I know the force of friction is 1.2 newtons. I know that that's mu times 4.905 newtons. So I know that mu is roughly, give or take, 0.24. That's choice A. It's not exactly, but that's the closest answer to what the calculation is. Right. So, again, we have this mass, we have a velocity, and we have our big red flag that it's moving around a circular track. Circular means centripetal force which means that I have these two equations to work with. And I have these, right? I have a velocity, I have a radius, I have a mass, so I can just plug in numbers. It's 1750 kilograms times 15 meters per second, that's squared, over 45 meters. And again, I do the math, I get 8,750 newtons, or choice C. Right, so far, most of it has just been math. Right, the first question was a little bit of thinking, but this is mostly just math. Right. Now again, number 5 is this kind of weird question. We have a 20 Newton force due north and 20 Newton force due east, as shown right here. I need to bring this to equilibrium. Right, now, if I need to bring this to equilibrium, I can't point north and I can't point east because that's how the forces are already going. I need to point opposite of them. So I can't point this way and I can't point this way. I need to point the other way. Not only do I need to point the other way, I need to cancel out everything that's happening. Which means I would need 20 west and I would need 20 south. But 20 west and 20 south is not the same as 20 southwest. Right? Because if you think about this, if I have to go this way and this way, then I actually need to make this side of the triangle. That's the hypotenuse. So I know it has to be southwest, but it also has to be 28 newtons. I can't just have 20, right? Because 20 southwest isn't enough to cancel all that out. Mathematically, I'm doing what we call a resultant force, which is something that I'll talk about after the quiz. But we're doing a resultant force, which means we're adding the forces together. We're just taking into account the fact that we're actually making a triangle. So we're looking for the hypotenuse. More on that later, but the bigger piece to this was that equilibrium has to point to the southwest. All right, number 6. The graph below represents the relationship between the force applied to the spring and the spring elongation for 4 different springs. So spring means spring force is K times X. Right? What has the greatest spring constant? Well, if I need to solve for the spring constant here, I'm going to do the spring force divided by X, that equals K. Now if I look at this, spring force divided by X, spring force divided by the elongation, that's the slope of this graph. Right? So if I'm looking for the greatest spring constant, I'm looking for the biggest slope. Because if you look at this, I have force on the y-axis, I have the elongation, right, the stretch of the spring as my x-axis. And if I'm looking for K, the only way I know how to do it is take force divided by elongation. That's the slope of this graph. Which of these is the biggest slope, the greatest slope? That's choice A. It also is the one that takes the most amount of force, and you only get a little itty bitty elongation, which means it's very difficult to do. And I think I said this, if I didn't say it before, I'm going to say it now. The spring constant is kind of a measure of like how difficult is it to stretch this spring, right? If it's really difficult to stretch the spring, we're going to have a big spring constant. If it's very easy to stretch the spring, it's going to be a small spring constant. Now, number 7 is a circle. Right. I'm just taking advantage of the fact that the centripetal acceleration is v squared over r, so I'm substituting. I know that I have 5 grams. I know my velocity is 2 meters per second. I know that I have to square that, so 5 times 4 is 20, divided by 0.7. 20 divided by 0.7 is a little more than, is almost 30. That's choice C. All right. Now number 8 is back to free body diagrams, right? Which diagram best represents the forces acting on the block? Well, I can actually say conclusively 100%, and they tell us, right? Friction normal force, and weight. I can tell that this is wrong, and I can tell that this is wrong, because these are not correct. Weight should point straight down. The other thing is that the normal force should be perpendicular to the surface, which means that it should point out like this. So here, this is wrong. So that's out of the question. It has to be choice D. I have the normal force pointing out of the surface, I have gravity pointing straight down, and I have friction pointing up the hill, because we're on Earth. Things want to slide down the hill. Right, number 9. Hello? Oh, there we go. It was a little delayed. Sorry, a little delay. So number 9 shows a block at rest on a horizontal frictionless table, and I need to know the force exerted on the block by the table. Well, the table is not pulling down. Those are off. Those are out of the question. The table is pushing up, but this is not a force. A shows the only force that's pointing in the correct direction. Right. Now, number 10, we have 2 carts pushed apart by an expanding spring. If the force on the left cart is 1 Newton, what's the force on the right cart? It's also 1 Newton. For every action, there is an equal and opposite reaction. All right. Let's keep looking. Let's keep going. Number 11, the force required to start an object sliding across a uniform horizontal surface is larger than the force required to keep it moving, right? An object in motion stays in motion. An object at rest stays at rest. Magnitudes of the size. Magnitude just means size. So the size of the required force is different in these situations because the force of kinetic friction. So kinetic is sliding friction. It's easier to keep something moving than it is to start moving it. So it's not going to be bigger than the force of static friction. It's actually going to be less. And you can use your table, right? The table on the very front page of the reference table will show you that all the kinetics are less than this force of static. Right here, we say that we are pushing it to the right. And we're talking about the force of friction. It always opposes motion. So if I push something to the right, friction is going to point to the left. All right. Number 13. We have a graph again. Elongations of a spring. Spring means this again, right? So we're looking for what is a spring constant. The only way that I know how to solve for that is if I do this. So I have a force of 8 newtons. I have an elongation of 0.4. That equals k, which means that if I do some math, I should get k equals 20 newtons per meter. Right. This was that. This was this. You can use any point except for 0, 0. That just means it seemed the most convenient. Right. It was the last one. It lined up very nicely. All right. Number 14. Lots of information. Blah, blah, blah words. Spring. All right. The magnitude of the force. How big is the force to compress the spring by this much? Spring constant is 140 newtons per meter. Okay. So the spring force is 140 newtons per meter times 0.04 meters. So that equals 4.2 newtons, if my math is correct. I'm pretty sure it is. Move it over 2, multiply by 4. All right. A 10 kilogram block, rubber block, is pulled horizontally on a sheet of ice. Calculate the magnitude of the force of friction. So I need the force of friction, which equals mu times the normal force. Lag. We're lagging. Okay. Mu times the normal force. The mu, I believe, is 0.15. The normal force, 10 kilograms times 9.81 meters per second squared is 98.1 newtons. This is the force of gravity, and that equals the normal force. So 0.15 times 98.1 newtons. If I do that math, it's a little unprepared today. Where'd it go? There we go. 0.15 times 98.1, 14.7. So my answer here, 14.7 newtons. This coefficient of friction seems wrong. Give me 1 second to come up with the, just to make sure. No, rubber on ice is 0.15. Okay. Just double checking that. Finally, calculate the magnitude friction between the road. So I have rubber tires. I have dry asphalt. I have a 1,200 kilogram car. So again, force of friction is mu times the normal force. Force of gravity is 1,200 kilograms. Times 9.81 meters per second squared. Well, this is 1,200 times 9.81. Oop. 4. $11,772. What happened there? There we go. 11,772 newtons. So I'm looking at rubber on dry asphalt is 0.67 times 11,772 newtons. And this is going to equal times 0.67, 7887, 0.24 newtons. Now you can leave the whole number. You can call it 7887 newtons. Call it 900 newtons, as long as you're within reason, right? What's reasonable, Mr. Cleveland? There's a spectrum there, but that, right? That was all the practice questions there. That's about all the different forces that we have, right? Friction, gravity, normal force. There's centripetal. There was spring force. The only one that didn't show up was the force of gravity, like between planets, right? Between really big objects. But again, it's going to be pretty obvious when you have to use that. Now, this video has gone on a little long just because there were more questions than usual, but this is, a good example of questions that you might see. Now, they should all look fairly familiar. If you have questions, please email me. Otherwise, next time I see you will be quiz day. Take care of yourselves, kids.